Good students, welcome to part one of the AP Calculus AB and BC multiple choice practice. We're going to be going over the first five questions. Let's go ahead and take a look at question number one. It says, which of the following defines a function f for which f of negative x equals negative f of x? So this is basically a representation of what an odd function is, okay? So odd functions are symmetric with respect to the origin. So if we take, there are two methods, two ways we can solve this problem. We can use the nature of the graphs to solve it, or we can just plug in negative x and see what happens, all right? So I'm gonna sketch these five graphs for you, just small sketches, and then we're gonna see which of them fits the definition of an odd function. Okay, so that's what we're gonna do. All right, now, all right, so let's sketch the first one. For y equals x squared, what does that graph look like? The graph of y equals x squared, the graph of a parabola, um, looks like this. It's good to know how your parent functions look like for the exam. All right, and then y equals sine x. I'm just going to draw one period to the right and one period to the left. The sine curve is basically like an S, like this. Going to the left and also going to the right. All right, so that is your sine curve. It's not a perfect sketch. And then for cosine, you remember what your cosine graph looks like. Similar, it's just like that sine x function, but it's translated. So you have your cosine function, one period to the left, and another period to the left. This to the right, this to the left. It repeats forever. Your logarithmic function, log base 10 function, looks something like this. Has an asymptote at x equals 0, intersects the x-axis at 1, and then it goes on like this forever. Okay, and then the exponential function is the inverse of the logarithm of the natural logarithmic function. So it kind of looks like this was reflected along the line y equals x. So the e to the x function looks something like this. All right, going in that direction. Okay. All right. Now let's take a look at all these graphs. Which of them has a graph of an odd function? An odd function is a graph that's symmetric with respect to the origin. Okay. Y equals x squared is even. It's an even function. It's symmetric along the line x equals 0. This is even. This is odd. Y equals sine x because it's symmetric about the origin, as you can see here. The cosine function is also even. This one is neither odd nor even, and this is neither. Okay. So this condition that's provided for us right here is the definition of an odd function. So the question is, which of this matches this definition? And clearly we can see that the only odd function here is option B. All right. So knowing what your graphs look like and their description, whether odd or even, can help you answer the question. All right, that's using one method, our knowledge of the graphs. Another way we can do this is by actually plugging in x and then using arithmetic to basically simplify it. All right, so let's start out by testing A. The question is f of negative x equal negative f of x? That's the question we're going to try to answer here. All right, so how about for f of x equals x squared, which is our option for A? If I substitute x with negative x, so I get the opposite of the original function. So negative x squared is x squared. So we can see that this is not equal to f of x. So we can see that this option A is not an answer. Okay. All right, let's go ahead and try B, which we determined to be the result using a graphical approach. We're now considering f of x equals sine x. Okay, we are answering the question. We're trying to answer the question is, it's not if, is f of x equal f of negative x. Okay, so what I'm going to do is replace x with negative x. All right, and then let's evaluate sine at negative x. Now, if you remember your odd and even identities for sine, you remember that sine of negative theta is equal to negative sine theta from trigonometry. Okay, so applying that here, this is simply negative sine of x. And guess what? This is equal to negative of f of x. All right, because f of x is sine x. So guess what? This is an odd function, and it meets the original requirement or the stipulation that was given here is f of x equal negative f of x. So the answer to question 1 is clearly option B. Okay? All right, so there you have it. Now let's take a look at question 2. It says the natural logarithm of x minus 2 is less than 0. It says the natural logarithm of x minus 2 is less than 0 if and only if. Well, this requires you to know the nature of this graph. Okay, the natural logarithm function, you need to know what it looks like, and also the whole idea of transformation. All right, so if you have this function right here, ln x minus 2, what kind of translation is this? Well, let's draw the parent function first, and then we'll talk about translation. Remember, your natural logarithmic function has an asymptote at x equals 0. Okay, so you kind of have an asymptote right here, a vertical asymptote right there, and it intersects the x-axis at x equals 1. Okay, so let's calibrate it 1, 2, 3. All right, so the parent curve, I'm going to draw it in dotted line. All right, so it intersects here because we know that ln of 1, natural logarithm, write that again, natural logarithm of 1 is equal to 0. All right, hopefully we see why that's the case, because we know that ln 1 is the same thing as e to the 0, right? And then using the power property of logarithms, we can bring this down to the front, and then this becomes 0, natural logarithm of e. The natural logarithm of e is just 1, so we have 0 times 1, which is just 0. Okay? All right, that's a general case. So we know that it intersects here, so the graph looks something like this. I'm going to try, let me use a dotted line to draw it, and then it curves like that. Okay? All right, so above the x-axis, the function is greater than 0, and below the x-axis, the function is less than 0. Okay? All right, so what does this x minus 2 indicate? Is a translation in the opposite direction. Since you have minus 2, that means you're going to shift 2 units to the right. You would do the opposite of what the number is next to the variable. If this were a plus, you go to the left. Since it's minus 2, this entire graph will shift 2 units to the right. Okay, so we shift this graph 2 units to the right. This intercept will move 2 places to the right. So it goes 1, 2, right there. And guess what? This vertical asymptote is also going to shift 2 units to the right, 1, 2. So our new asymptote is going to be right here. Okay? Now this is what the translated graph is going to look like. It's going to look something like this. Like that. Okay? Alright, this right here is ln of x minus 2. And this right here is ln of x. This is a parent function. This is a translated function. Okay? Now the question is, when is this function less than 0? Or when is it beneath the x-axis? Okay? This is where it's less than 0. Let me just show you a region. So from here all the way down, it's less than 0. Okay? From here down, it's less than 0. All right? Let me just change the color of that real quick. So for that region is less than 0. So the question is, take that red, good. So here is when ln of x is less than 0, where f of x is less than 0. So for what values of x in this function is the graph beneath the x-axis? We can see that it's constrained to this interval right here. Let me put the numbers in so we see what's going on. So this is 1, right? And then this is 2, and this is 3. All right? We started from 1 and shifted 2 units to the right, so that took us 1, 2, all the way to 3. So you can see that between 2 and 3, the function is beneath the x-axis. All right, so between these boundaries right here. All right, so how do we write that using inequality notation? This boundary between 2 and 3 can be written as the lower bound, which is 2, is less than x, and x is less than 3. So this is where this function is less than 0. Okay? Remember, we have an asymptote here, and this point is excluded because it is equal to 0 when x is equal to 3. All right, so your answer is option C. All right, let's take a look at question number 3. And question 3, we have a function right here with a removable discontinuity, and we're asked to find a k-value that makes this function continuous. What k-value will fill in this discontinuity? That's a question we're going to solve. All right, so it's simply easiest way you can do this is basically set k to equal to this function, and then substitute the value where the discontinuity happens. Okay. So before we do that, we're going to try and remove the removable discontinuity by simplifying it. So we're going to go k, this function right here, the point equals the square root of 2x plus 5 minus the square root of x plus 7. Okay? That divided by x minus 2. All right, there should be a removable discontinuity here, which is basically a factor that we can cancel out to get rid of this denominator, this discontinuous value. But in order for us to find that, we need to first of all simplify this. Well, how do we do that? We just multiply the numerator and the denominator by the conjugate of this expression on the top. All right? So you get a conjugate by simply taking the opposite of the sign in the center. So I'm going to multiply the top by the square root of 2x plus 5. And then change this minus to a plus the square root of x plus 7. And then the denominator I'll multiply it by the same thing. The square root of 2x plus 5 plus the square root of x minus x plus 7. Okay? All right, so I'm going to, if you distribute the top using difference of squares formula, we all know that a plus b times a minus b, well, let's reverse the order. A minus b times a plus b is equal to a squared minus b squared. Okay? So using this idea on the numerator, the numerator is going to simplify basically to, we have k equals the square root of 2x plus 5 squared minus the square root of x plus 7 squared. And then this whole expression divided by x plus 2 times the square root of 2x plus 5 plus the square root of x plus 7. Okay? Don't bother distributing the denominators. It's a total waste of time. Don't do that. All right? So let's simplify the numerator. So what are we going to get? Well, let's see. In the numerator, the square and the square root cancels out, as you can see here. And they're going to have 2x plus 5 minus x minus 7. Don't forget to distribute this minus to this plus right here. Divided by the denominator, let's leave that alone. Hopefully this, oh, I switched the sign. Hopefully this x minus 2 cancels out. It's too big. Make this a minus. Hopefully this x minus 2 that we have over here cancels out. X minus 2, so let's do x minus 2. All right, so leave this alone the way it is. The square root of 2x plus 5 plus the square root of x plus 7. Okay? All right, simplifying the top, you can clearly see that it's going to become x minus 2. 2x minus x is x. Positive 5 minus 7 is 2. You have x minus 2 in the numerator over x minus 2 times the square root of 2x plus 5 plus the square root of x minus x plus 7. Okay? Now, x minus 1 goes here 1, x minus 1 goes here 1, so you're left with 1 over the square root of 2x plus 5 plus the square root of x minus x plus 7. Okay? All right, this is the k value that we want k to assume in order to fill out that removable discontinuity. So to finish this problem off, all we simply do is we're going to plug in the x value that caused that discontinuity to happen. Okay? Let me write this down. 2x plus 5 plus square root of x plus 7. So what was the x value that caused the removable discontinuity to happen? It was x equals 2, right? See right here? The value that x cannot be, that's where the discontinuity happens, is x equals 2. So what I'll do is I'll plug in 2 into the right side here, and then whatever value of k I get, that's my answer, all right? So I'm going to evaluate k at x equals 2, so we're going to have 1 over the square root of 2 times 2 plus 5 plus the square root of 2 plus 7. If you simplify that, you have the square root of 2 times 2 is 4, plus 5 is 9, square root of 9, plus the square root of 9, which equals the square root of 3 plus 3, which equals 1 over 6. Okay? So your answer is 1 over 6. This is the k value that will guarantee that this graph has no removable discontinuity at x equals 2. Or actually anywhere on the domain. Okay, so our answer is option B. Alright. Alright, so for number 4, let's take a look at number 4. This is a integration problem, definite integral. We're going to be using use substitution to evaluate this integral. So we evaluated the integral, find the antiderivative of, let's rewrite this as 1 over the square root of 1 plus x dx, evaluating this definite integral from 0 to 8. Okay? So how do I know that it is a use substitution problem? Well, if you look at this is a composition of a radical function and a linear function. And if I differentiate this inner function right here, I'm going to end up with dx. Okay? All right, so what I'm going to do here, I'm going to set u. U is going to be the inner function. So let me show you what I'm talking about here. I'm going to have u be, this is green, the radicand, which is 1 plus x. Okay? And note, if I differentiate this, the u is simply going to be derivative of 1 is 0, derivative of x is 1 dx. Okay? So if I make that substitution, I'm just left with dx, and then I can replace that with du without any problems. All right? So before I make this substitution, let me rewrite this function. I'm going to write it as the antiderivative from 0 to 8 of 1 plus x raised to the negative 1/2 power. Okay, using law of exponents. All right, so this inner function right here, 1 plus x, the linear function, if I differentiate it, I'm going to be left with dx, with a multiple of dx. If that happens, then you can use substitution, okay? All right, so let's make the substitution. I'm going to write this as the antiderivative. Remember, these are limits on x. This is x equals 0 as a lower limit and x equals 8 as the upper limit. So I'm going to express this as 1 plus x is u, so it's going to be u to the negative 1/2. Dx is simply du. So this is a nice substitution. And our limits are going to change. When x is 8, the upper limit, that implies that u, which is 1 plus x, is going to be 1 plus 8, which equals 9. So our upper limits will increase by 1, which is 9. U equals 9 now. And our lower limit, x equals 0, that implies that our lower limits of u is going to be 1 plus 0, which is 1. So it's going to shift from 0 to 1. Okay? All right, now let's evaluate this integral. It looks much nicer. Now using the integration rule, we're going to integrate this. This is going to become u to the negative 1/2 plus 1. Negative 1/2 plus 1 is simply, well, let me just show you the steps. Negative 1/2 plus 1 over negative 1/2 plus 1. Okay? Evaluating that from 1 to 9. All right, and now what does that yield? We're going to have, it's going to become u to the 1/2 over 1/2 evaluated from 1 to 9. Okay? Now we can multiply the numerator by the reciprocal of the denominator. So that becomes 2u to the 1/2 evaluated from 1 to 9. Okay. We can even factor out the 2 since it's independent of the limits of integration. So u to the 1/2 evaluated from 1 to 9. So we just use FTC part 2 to finish this off. Okay, so it's going to become 2 times, plugging in the upper limit, 9 to the 1/2 minus 1 to the 1/2. Okay, and that becomes 2 times 9 to the 1/2 is just the same thing as the square root of 9, which is 3, minus 1 to the 1/2 is 1. And then we have 2 times 2, and our answer is 4. Okay, so there you have it. All right, so scroll up. Our answer is option D. Option D is our answer for this one. All right, let's move on to the last question. Question number 5. It says if 3x squared plus 2xy plus y squared equals 2, then the value of the y dx at x equals 1 is. So in this one, we're basically going to use implicit differentiation since this is an explicit function. So let's go ahead and use implicit differentiation to find what dy dx is, and then we'll evaluate the derivative at x equals 1. All right. So we have 3x squared. We want to find d dx of 3x squared plus 2xy plus y squared equals d dx of 0, d dx of 2. Okay? All right, let's do it. So this one we're going to use the power rule to differentiate that. So using the power rule here, we're going to have 3, factoring that out, differentiating this is going to be times 2x. And then the derivative of x, we have times dx. Okay? Plus, now if you look at this 2x, we have two functions, so we're going to use the product rule here. Okay? So this is u, and this is v, right? And remember, u v prime, the product rule for finding the derivative is basically u v prime plus vu prime, right? So that's what we're going to do here. So first of all, factor out the 2. Let's put that 2 on the outside. And then we have u is x, v prime. The derivative of y using the power rule is just 1 times dy dx, applying the chain rule, plus v is y. Derivative of x is 1, applying the chain rule, dx dx. And then we close that up. Now differentiating this, derivative of y squared using the power rule is 2y, dy dx. And then using the constant rule for 0, d dx of 2 is simply 0. Okay? For 2, yeah. Anyway, there you have it. Okay, let's simplify this. So we're going to have 3 times 2 times 6. 3 times 2 times x is 6x. The x dx just reduces to 1, plus 2 times x dy dx plus just y plus 2y dy dx. Okay? Dy dx equals 0. Now the goal here is to, let's simplify it first and then I'll tell you what the goal is. So let's simplify this piece with the parentheses. I'll just distribute these two terms here. So we're going to have 6x plus 2x dy dx plus 2y plus 2y dy dx. Okay? Equals 0. Now let's isolate the terms with the dy dx. So I have to move 6x and 2y to the other side. And I will factor out dy dx. Okay? So let me just show an intermediate step. So 2x dy dx plus 2y dy dx equals negative 6x minus 2y. Okay? There you have it. So let's factor out the dy dx on the left side here. So if we do that, what are we going to have? We're going to have dy dx factored out times 2x plus 2y equals negative 6x minus 2y. Okay? So now what I'm going to do next is divide both sides by 2x plus 2y. That basically gets rid of that. So let's do that. 2x plus 2y sides. All right, so there goes dy dx. Okay, so dy dx is basically negative 6x minus 2y over 2x plus 2y. All right, but this problem, we are asked to evaluate this function at x equals 1, okay? But if you notice, this derivative is dependent on x and y at x equals 1. So we need to know the y value when x is 1 of the original function in order to evaluate this derivative at x equals 1, all right? So how do we do that? Well, we have to substitute 1 into the original function, which is 3x squared plus 2xy plus y squared. We're going to plug in 1 here for x and then isolate y. Okay, so let's do that. So we have 3 times 1 squared plus 2 times 1 y plus y squared equals 2. All right, simplifying this, we'll have y squared plus 2y plus 3. And if you subtract 2 from both sides, I'm subtracting 2 because I want to write this as a quadratic equation in standard form, right? Plus 1 equals 0. Okay, now let's factor this out. I like to use my little x game to factor quadratic. So AC goes on top. AC is 1, and B is 2, goes on the bottom. So two numbers that work here, 1 and 1. These two numbers times to give you 1 and add to give you the bottom 2. So if we want to factor this, we'll have y plus 1 times y plus 1 equals 0. You see we have a double root. So if y plus 1 equals 0, that implies that y equals negative 1. All right? So we're going to be, the derivative that we had dy dx equals negative 6x minus 2y over 2x plus 2y. We're going to evaluate this at a point where x is, what was x? Let me see, I forgot already. X is 1 and y is negative 1. Okay, we're going to plug in these values here and then see what the derivative is. So it's going to be negative 6 times 1 minus 2 times negative 1 over 2 times 1 plus 2 times negative 1. Okay? And if you work this out, you have on the numerator negative 6 plus 2 over, in the denominator, 2 minus 2 is 0. You're dividing by 0, so the derivative is basically undefined here. Okay, because you can't divide by 0. You're going to have a vertical tangent line at this point. All right, so our answer is option letter E, not defined. All right, so that's that. But thanks so much for taking the time to watch this presentation. Feel free to subscribe to my channel for other parts by clicking up here, and click like if you like this clip. And please post a comment to let me know what you think about this presentation. More clips coming from at GoodServe.com. Thanks again and have a wonderful day.